Hello everybody. So in this video we are going to solve the exercise 3 from the problem list in plotting functions. So this exercise is a natural continuation of exercise 2. So now we have more things on double roots. In this particular exercise we have to plot the polynomial p of x, which is equals to 2 times x plus 1 squared times x minus 1 for the domain of x minus 3, 3, both limits included. In this case using a blue solid line. We have to plot in the same figure also its derivative using a red solid line and the x-axis with a black solid line. In this case, the statement is very similar to the exercise 2. And then we have 3 questions that we are going to solve once we have plotted the functions. So we go to Matlab and we proceed in the same way as we have done in exercise 2. We open a new script. We save this script, in this case with the name problem3.m, and we start clearing our workspace. We close all the previous figures and we start at the top of the command window, or alternatively you just can clean the command window entirely. So as we did in exercise 2, we construct first the vector of the axis x. So we need the initial point, -3, the final point, 3, and the number of points that we want to use. So let's go for 200 in this case. And then we construct the vector calling the function linspace. It's a built-in function in Matlab that needs a first argument, which is the initial point, a second argument, which is the end point of the vector, and the number of points that this vector will have. Once we have the vector x, we have to construct the function, in this case the polynomial p, that is 2 times x plus 1 squared. So be careful here. Remember that we want a vector as an output of our operation, right? We are not using the x here, this array. Using algebraic operations, we want component by component operations. So the power operator needs the point in order to be computed component by component. And also this product needs the component by component definition, such a way that this is a vector. When we do component by component power 2, the result is a vector, and then this vector will multiply component by component to another vector, and the final result is the vector that corresponds to the function p. We also need the derivative, so we proceed exactly in the same way. In this case, the derivative will be 2 times x plus 1 times x minus 1 plus x plus 1 squared. And I missed a parenthesis somewhere. Okay. So we also need the x-axis. So as we did in exercise 2, this is simply a vector full of zeros with the same size as vector x. So now that we have the 3 lines that we want to plot, we call the plot function. Firstly, we plot the function p using a blue solid line, then the derivative of the function p using a red solid line, and finally the x-axis using a black solid line. And we can format the plot using the legend, where firstly we plot the function p and then the derivative of the function p. So we can run this. And I did a typo here. So let's run it. And this is what we have. The function p here in blue, the derivative of the function p in red, and the x-axis. So let's go to the statement and let's answer the 3 questions. The first one is, how many roots does the polynomial have in that interval? So in -3, 3. And you can see if we zoom in a little bit, that the polynomial, this blue line, has just 1 root here and 1 root here. So it has 2 different roots in the interval -3, 3. And the derivative has 2 roots, 2, in the interval -3, 3. And do they have something in common? The answer is yes, because one of these roots, which corresponds to x equals to -1, is a double root. Because at this point, the function and the derivative both vanish. And here, we don't have a double root. We simply have a single root, because only the function vanishes at the point x equals to 1. So this is the solution of this exercise. Thank you.